Within Foundations 30, we also do a unit on polynomials, exponentials, and sinusoidal functions, or exponential and logarithmics. So what we're going to do is it all comes under one specific outcome that's 30.7. So it does a lot of analysis of data and representations. We're only going to focus on one point of it, because the amount of material for each of these specific things, for example, polynomials, and then the logarithmic exponential, and then the sinusoidal functions, there's just so much in them. It would blow your minds to have to do all of those concepts as once. So we're only going to focus on polynomials at first, and then we'll go into the other two later on. So here are our outcomes. We're going to do some analysis of graphs and talk about their characteristics. We're going to graph. We're going to talk about some technology. I like encouraging the use of not relying strictly on technology, but also you being able to graph things by hand. We're going to talk about, again, on their characteristics with relation to their equations, and talk about degrees and signs and so on, in order to demonstrate mastery of these polynomials. And one thing, now, if you've taken Pre-Calc 30, you'll notice that these things are very closely related to each other. The biggest distinction between the Foundations 30 and the Pre-Calc 30 is Foundations 30 strictly keeps the degrees of equations less than or equal to 3. Now, of course, I like making the connections to the higher degree functions, but Pre-Calc 30 is, or sorry, Foundations 30 only sticks to less than or equal to degree 3 for assessment. So to be able to understand, you have to be able to do all of those things. You have to deal with characteristics, interpreting graphs, and do a whole bunch of different things like that. It's a huge mastery outcome. Now, as I said, there's a lot of relation. So if I'm the one that had taught you Pre-Calc 30, it's going to look very similar. So we're going to talk about the characteristics first, and we're going to talk about in relation to their equations. So a polynomial function is a function of the form an x to the power of n plus an minus 1 x to the power of n minus 1 plus a, so on and so forth. All that means is the n for the exponent is a whole number. So it can't be any fractions, can't be any decimal, can't be any negatives, it has to be a whole number. So your whole numbers, just tying back to your number systems, which we kind of started talking about, I would have started talking about at grade 9. Whole numbers, 0, 1, 2, 3, so on and so forth. Your x is a variable. The coefficients an all the way to this a0 are any real numbers. So you're just not dealing with any of the complex numbers. Again, kind of started talking about that grade 9, a bit more in grade 10, so on and so forth. So some examples would be like this. Our f of x is 2x plus 1, or f of x is x squared plus x subtract 6, or y equals x cubed plus 5x squared minus 3x add 6. So those are all examples of polynomials. Our first example is we are going to identify whether each function is a polynomial function or not. And we're going to justify our answer. So first things first, this is going to be a nice flashback, and we're going to deal with this kind of equation or type of idea when we talk about our exponentials. But this x in the denominator is x to the power of 1. So if we tie back to what we had done in grade 10 in Foundations Pre-Calc 10, this being in the denominator, in order to put it to the numerator, if you're taking the reciprocal, it would become a -1. And by the definition, the n, that exponent, has to be a whole number. -1 is not a whole number. So because it's not a whole number, this is not a polynomial. Y equals 3x squared minus 2x to the power of 5 plus 4. Now, even though it's not written in proper descending order, you can see that all of our exponents are whole numbers. The x's are variable. The coefficients, meaning the numbers in front, are all real numbers. 3, -2, +4, those are all real numbers. So we're good. That is absolutely a polynomial function. Our next one, y equals -4, x to the power 4 minus 4x add 3. Again, all of the exponents, even though this one isn't stated, is an exponent of 1. And technically, this is actually an exponent of 0, same thing as this one, which means that all of our exponents are still whole numbers. X is a variable, and our coefficients, -4, -4, and 3. Yep, that makes this a polynomial function. And our one over here, x to the power of 1/2 subtracting 7. Well, 1/2 is for sure not a whole number. So since the 1/2 is not a whole number, this is not a polynomial function. In Foundations 20, we had started talking about some standard form. Now, the 4 types of polynomials that we've concerned ourselves with in Foundations 30, we have these strict standard forms for them. There is the constant term, or the constant polynomial, which is a y equals some kind of number. Sometimes people will write it as just y equals a, but a is just a number. You have a linear function, which you had started working on in grade 8, further into grade 9, and for sure been able to graph them in here, in grade 10. Now the connection, the more standard version you may remember is it being y equals mx plus b. So m being your slope, b being your y-intercept. A quadratic is what you had done in Foundations 20. And this is the standard form for a quadratic. It's ax squared plus bx plus c. Again, just like the definition of a polynomial, all of our exponents have to be whole numbers, x's are a variable, and the coefficients are just some real numbers. So that a, b, and c are some real numbers. Now, Foundations 30, we go one step further. In pre-calc 30, we actually go 3 steps further. So a cubic just has an ax to the power 3, add bx to the power 2, add cx plus d. Now, of course, you don't need all of these, but the key aspects in each of these is in order for it to be a cubic, you need to have an x cubed. Just the same as the key aspect for it being quadratic, it has to have an x squared. Linear has to have an x, and a constant has to have a number. The rest of these parts are actually not necessary, because you could technically have 0 as your b value or 0 as your c value, and you still have a quadratic or a cubic, depending on which one I had made a 0. So we'll talk about a few more definitions, a few characteristics of these polynomials, and these are actually things that we had done in grade 9. So the first one is the degree. The degree of the polynomial function in one variable x is n. It is the exponent of the greatest power of the variable x. So the degree in a cubic is just basically our highest exponent. If we go back out here, our highest exponent here is a 5. Now, of course, that one is higher than what we do in Foundations 30, but it would me being able to say that, yes, our degree is 5 is not a stretch for a grade 12 level course. The coefficient of the greatest power of x is called the leading coefficient. So whatever number is in front of that variable that has that highest degree is known as the leading coefficient. The term whose value is not affected by the variable is known as a constant term. Meaning, if it's not affected by a variable, it also means that there is no variable. What do I mean by that? the number 4, the number 3, the number -7. Even though this is not a polynomial, it's still this would be considered the constant term. But if we go back to here, there is really no x to the power 0, even though x to the power 0 is just 1, tying back to our exponent laws from grade 9. But this is our constant term. It's a number that doesn't have a variable. It's not affected by a variable. One thing that you need to know, though, and we had done in Foundations 20, is talking about the constant term being the y-intercept. So we had talked about this c value in Foundation 20 being the constant value or constant term. It's our y-intercept. Now here's somewhat of a new kind of concept, but it's not a huge stretch. It's talking about what's known as the end behavior. Now an end behavior refers to the quadrant that a function starts and ends in. You always read from left to right. When we talk about quadrants, we talk about the first quadrant being in the top right, second quadrant being in the top left, or sorry, at top left, sorry. Third quadrant, bottom left, and fourth quadrant in the bottom right. Now, of course, I've always been privy to using Roman numerals. I'm fine with you saying 1, 2, 3, 4 as well. Just remembering it does go counterclockwise and starts up in the top right. So here's what we're going to do. We're going to talk about what the degree is, the leading coefficient, constant term, and we'll talk about end behavior when we talk about what their characteristics are. So I'm just going to set up something nice and fancy here. Let's talk about the degree. The leading coefficient, and the constant term in each of these questions. So our degree in this polynomial is the polynomial whichever has the highest exponent with variable x. So in this case, our degree is 1. It's the only variable it has an x, and the exponent is 1. And the second one, now let's just talk about all degrees first. Our highest exponent here is 2. And our highest exponent in the last one is the 3. The leading coefficient is whichever coefficient is in front of that greatest power of x. So whatever number is in front of that thing that has that degree is known as the leading coefficient. In this one, it's number 2. In this one, it's the number 1. Because even though it's not stated, there is a 1 there. And in this one, it's the -3. The entire variable, or sorry, entire coefficient in front of that variable. And last but not least, we talk about the constant term. And the constant term is one that's not affected by a variable. In other words, it doesn't have a variable. In this one, it's 1. In this one, it's that entire -6. And in this one, it'd be a +6. Just as a word of caution, if by chance this did not have anything into it, so if it did not have this @6, we would have a constant term of 0. So keep that in mind. Alrighty, let's talk about some graphs, talk about a few different things. Now, of course, I will make specific note, this is a pre-calc 30, but I like using these graphs to help illustrate a point. For Foundations 30, we talk about linears and we talk about cubics. The polynomial function in their graph can be analyzed by identifying degree, end behavior, domain and range, and the number of x-intercepts. So first things first, let's look at the degrees of each of these. Now you'll notice each of them does have an equation with them. They may be a little bit small and not be the greatest to read, but they are there and you just have to take a good look at them. So first things first, what is the degree of our linear? Well, it's actually pretty identical to the one just on the previous page. It's 2. Sorry, 1. Oh. I'm thinking of the leading coefficient, sorry. Degree is 1. The degree here is at 3. And our degree in this one is 5. Now I have set up these specific graphs to help illustrate another point. To illustrate another point. They do not always have to look specifically like this. This is just one way that these look. So with a linear function, the maximum number of x-intercepts that this linear function can have, well, is the 1. For a cubic, we can see that there's 1, 2, 3 x-intercepts. And that is also going to be the maximum amount of x-intercepts that a cubic can have. For a quintic, again, it's not necessary in Foundation 30, but it's useful to help illustrate the point. In this cubic, there's 1, 2, 3, 4, 5 x-intercepts. Hopefully, you start seeing a little pattern here. Now, end behavior. Now, I'd mentioned end behavior being one of our definitions on this page, so we'll bring back to it. So an end behavior refers to the quadrants that a function starts and ends in. It is read from left to right. So if we talk about our end behavior, again, 1, 2, 3, and 4. This linear, first thing, to know whether something is a positive or negative, you need to look at the leading coefficient. And if our leading coefficient is positive, like this one, it's a positive 2. What is its end behavior? Well, you can see it's starting down the bottom left and ending in the top right. Bottom left to top right means it's starting in quadrant 3 and it's going all the way to quadrant 1. Now, since we have the end behavior for a linear, we can look at the end behavior for the cubic and for the quintic and see that each of these are also starting down in quadrant 3 and ending in quadrant 1. Keeping in mind, if we look at the coefficient in front of the cubic, it's a 1, and the one in front of the quintic, it's also 1, both being positive. So each of these end behaviors is going from quadrant 3 to quadrant 1. So if we by chance had a negative leading coefficient, like this, for a negative line, so if we have a negative line, so we'd have a negative mx plus b, or standard form would be ax plus b, but a would be negative. It's going from quadrant 2 down to quadrant 4. Likewise, if we had a cubic, I'll just draw one specific type of example, that being a cubic, you'll notice a few things, and I'll actually tie back to the boxes that are just right above, talking about the maximum number of possible x-intercepts. You'll see in this one, there's actually only one x-intercept there. It's only crossing the x-axis once. But this would just have a leading coefficient that would be negative. But you'll see the end behavior is still the exact same. It's starting up in quadrant 2 and ending down in quadrant 4. For a quintic, so sorry, just go back one more thing. So our maximum number of x-intercepts. Now we do have a minimum number of x-intercepts for these linear, cubic, or quintic polynomials. But a quintic could possibly have 1, 2, 3, and if it just touches, it could actually have 4 x-intercepts. But a negative quintic has the exact same end behavior as a negative linear and as a negative cubic. It starts in quadrant 2 and ends in quadrant 4. Now we'll go back to grade 10, Foundations Pre-Calc 10, when we started talking about domain and range. Domain being our x values and our range being our y values. If you have difficulties remembering what is your domain and which is your range, you can always treat it as alphabetically. D comes before R, X comes before Y. So if we look at our domain on the positive linear or even the negative linear, you'll notice that this arrow means it's going left. This arrow means it's going left. This arrow is going right. This arrow is going right. So because it's going left and it's going all the way right, in set notation, our domain is x such that x is an element of the real numbers. It's going over every single possible x value. If we look at the domain on the cubics or the quintics, you'll notice that they have the exact same type of characteristics. This arrow is going left, well, this one's going left. This one's going right, this one's going right. These ones are going all the way from the left, all the way to the right. So they have the exact same domain as a linear. I like set and interval notation. There are more concise ways of doing it. This just helps deal with a lot of overlying concepts that we do in mathematics. Now we talk about a range. Well, just like our arrows going left and going right, the arrows are also going up and down. Each and every single one of them is either starting down and ending up, or starting up and ending down. But no matter what, it's going over every single possible y values vertically, because y values are vertical. But it's going over every single y value, which means our range, just like our domain, is all real numbers. The only difference is its y values, not the x values. So that's what linear, cubics, and again, quintics look like. If we talk about these types of shapes, so quartic is the pre-calc 30 extension, again, to help illustrate a point and illustrate ideas. Our degree of a constant term, well, I know that you can already read it. It is degree 0. But the other way of noting it is that it is an x to the power of 0. So meaning the degree of the constant term is 0. The degree of a quadratic is its highest power, which is 2. Yes, I know you can read that it's 2. Quartic is 4. The maximum number of possible x-intercepts for a constant term, this is actually the trick to it. This is actually a trick question. There's potentially an infinite amount of possible x-intercepts, because this line could be lying right on the x-axis, which means that there would be an infinite amount of x-intercepts. But that's a trick question, kind of, a little bit. Anyways, the quadratic, which we had done in Foundations 20, well, you can see it specifically right here, that there are 2 x-intercepts. A quartic, there's 1, 2, 3, 4. Again, just like we talked about whether it's a positive or negative, by the leading coefficient, you'll notice here, so sorry, I'll just write down my quadrants again, 1, 2, 3, and 4. For a positive constant, well, are positive because it's a positive 3. You'll notice that's starting up in quadrant 2 and ending over in quadrant 1. The quadratic, also a positive 2 being our leading coefficient, it's also starting in quadrant 2 and ending in quadrant 1. And a quartic, same characteristic. If by chance we had negative leading coefficients, so if our f(x) was, say, negative 2, so if f(x) was, say, negative 2, or if we change this to be a negative 2x squared, it actually had to be, we'll change it to plus 3. The negative quadratic would look like that. Quartic, that's one possible way that it could look like. But in each of these, you'll notice that starting down in the bottom left and ending in the bottom right, which means its end behavior is quadrant 3 to quadrant 4 in every single one of these cases. Our domain, well, all of these, the arrows mean they're going left and they're going right. Every single one of these polynomial functions has a domain of x being an element of the real numbers. Our range, though, is a little bit different. This one is one thing that is very different, because you'll notice that this one only has one strict range. Now, I want to talk about just every single general constant quadratic and quartic type of shape. In general, our range is going to be dependent on our equation. Because on this on the positive quadratic, it'd be y's that are greater than or equal to negative 3. On the negative quadratic, it'd be y's that are less than or equal to positive 3. On the positive quartic, it'd be all of our y's that are greater than or equal to negative 7. On our constant term, it's all our y's that are equal to 3. So it depends on what the equation is. So hopefully we're able to see some characteristics between this page and this page. Hopefully you identify that this entire page has all odd degrees. 1, 3, 5 are all odd numbers. 0, 2, and 4 are all even numbers. And there's special characteristics for their end behavior. Now you can say that even powers, yeah, are going to have even amount of possible x-intercepts. Or in the case of a constant, technically an infinite amount. The odds have a maximum number of x-intercepts according to their degree. Linear is 1, cubic 3, quintic 5. The end behavior for each of these. And I do like you to commit these to memory because it's really easy to do as soon as you have it memorized. If you have an odd degree and the leading coefficient is positive, it's always going to be going from quadrant 3 to quadrant 1. The way that I always like treating it or looking at it is a line. If you have a positive line, which is an odd degree, it's always going to be going from quadrant 3 to quadrant 1. If you have an odd negative, so an odd degree with a negative leading coefficient, that's actually going from quadrant 2 to quadrant 4. Because if you have a negative line, it's starting up in quadrant 2 and ending down in quadrant 4. If you have an even positive, the way that I always like dealing with even positives is I think of parabolas. I know that some people may think of constant terms, because if you have a positive constant, yeah, you're above the x-axis, which means you're going from quadrant 2 to quadrant 1. The reason I like talking about quadratics is because we deal with them so heavy in Foundations 20, and well, a lot heavier in Pre-Calc 20, and Pre-Calc 20 being really one of my favorite courses, just because there's so many quadratics. I have another fun story on that one, but that's better left for in class. If you have an even negative, so if you have a negative parabola, well, a negative parabola looks like that, which means it's going to be starting in quadrant 3 and ending in quadrant 4. You may have also noticed some other characteristics. For example, positive leading coefficients, they always end in quadrant 1. They always end up. So that's one way to know if you have a positive polynomial. If its end behavior ends up on the right, you have a positive coefficient. The exact opposite is also true. Negative polynomials end in quadrant 4. They always end down. So negative is down, positive ends up. Another way of dealing with it. Now, if you need to know a few other things, odd degrees always end on opposite sides of the x-axis. Or sorry, their end behavior is always on opposite sides of the x-axis. Quadrant 3 starts down and ends up. An odd, for a negative, starts up and ends down. Even degrees start and end on the same side of the x-axis. It's positive, starts up, ends up. If it's even and it's negative, starts down, ends down. So let's look at just some equations to see what our characteristics might be. We just want to determine what quadrant the graph in each of these polynomials begins and finishes. Now I know that these are way above what Foundation 30 is required to do, but again, it's dealing with the pattern. If we identify two key characteristics, we can determine whether it's going to be doing what our end behavior is going to be. Those two characteristics are what is the degree and what is the leading coefficient. The degree here is 15. The leading coefficient is 1. More specifically, the degree is odd. The leading coefficient is positive. If you have an odd positive, you have to think of a line. Well, lines, a positive line looks like that, which means it's going to start in quadrant 3 and end in quadrant 1. In this one, we're going to do the same thing. Identify what the degree is, identify the leading coefficient. Our degree is 10. Our leading coefficient is -1. But we don't really care what the numbers are, at least not too much. We care that this degree is an even number, the leading coefficient is negative. If you have an even negative, that means you're dealing with a parabola that ends down, which means our end behavior is quadrant 3 to quadrant 4. And that's how you can deal with the characteristics of the equation to find out end behaviors of polynomial functions. All right, a few more things. First thing, we're going to identify a few characteristics of each of these different graphs, and we're going to match the equations to the graphs. So we have a whole bunch of things, and we're going to talk about the graphs. So first off, we're going to talk about what type of function we have, whether it's even or odd. So the type of function, this one, again, it's dealing with a few more things. It has 1, 2, 3, 4, 5. This one is not in our specific Foundations 30 curriculum because of how many x-intercepts it is. But what we can identify is whether its degree is going to be even or odd. And this one, because it starts up and it ends down, it's starting and ending on opposite sides of the x-axis. It's an odd degree. The end behavior is starting up in quadrant 2 and it's ending in quadrant 4. This one, yes, it has 5 x-intercepts, and our y-intercept, it's really hard to read, but it's actually 0. So of the equations that would actually match with this, the only odd degree polynomial that would have end behavior going from quadrant 2 to quadrant 4, meaning it would have to be negative with 5 possible x-intercepts and 0, the way that you can always look at your y-intercept. It's always your constant term of your equation. The only one that matches is C. If we look at the next graph, we can see, yeah, there's 2 possible x-intercepts. Don't really care too much, but this one, because it starts below the x-axis and ends above the x-axis, this one is also odd. Specifically, and the extension, this one you can know, is cubic. The end behavior, starting in quadrant 3 and ending in quadrant 1, meaning the leading coefficient is positive. It has a maximum number of x-intercepts of 2, and the y-intercept in this one may not be the easiest to read, but it is 3. The only one that matches that is equation B, with that degree of 3 and a y-intercept of 3. Alrighty, next one. Is this even or odd? Well, it's starting below the x-axis and it's ending below the x-axis. Because it's starting and ending both on the same side of the x-axis, it would have to be even. Its end behavior, so starting down in quadrant 3 and it's ending in quadrant 4, it has 1, 2, 3, 4 x-intercepts. Our y-intercept hard to read, it would actually be -4. The only one that would actually match with that, and the only reason I know this, sorry, first off, because it's ending down, it would have to be a negative. The only reason I know that it's -4 is because of this equation. This is the only equation that matches as a leading coefficient of negative. So y-intercept is -4, and it's an even-powered polynomial. Obviously, by process of elimination, this would be D. But let's identify the key characteristics. It's starting and ending above the x-axis, which means it would have to be an even polynomial. Starting in quadrant 2 and going to quadrant 1, because it's ending positive, its leading coefficient would also have to be positive. This one has 1, 2, 3, 4 x-intercepts. Its y-intercept is -12. Why do I know it's -12? Because of the equation. The only even-powered polynomial that has a positive leading coefficient is this one. It would have a y-intercept of -12. And there's our characteristics. Now, as you go and have fun, I know the textbook uses some turning point stuff. I don't necessarily ask you for turning points on any of your assignments, so you can kind of leave that one out. Some people do strongly encourage it, but I don't find that it makes a huge difference for foundation study. All right, now you can go have fun.